Okay, what are our two special trig limits that we always rely on? Okay, good. So the limit of sine, I'll call it theta, sine theta over theta as theta approaches 0 equals 1. Good. And then we also have a second one, the limit of what, 1 minus cosine theta? Yeah. Over theta as theta approaches 0 equals 0. Good. So those are the two we know, right? Okay, so then if we know those two and we want to maybe leverage those, when we can, we will, but it won't work every time. For a problem like this guy, it's not going to work. How come? You can see right away that neither of those are going to fit here. They're going to fit well. Let me grab this guy and make it bigger. That doesn't match up well with either of our special limits, does it? They're using phis there, doesn't that? I mean, phi theta doesn't make any difference. This is just a different, it's like a, x versus y, just different angular variable. A lot of times in math and physics, we'll want to use lowercase Greek letters for our angles. A lot of times we'll use theta a lot, phi a lot, we'll use alpha, things like that. But what's not working there? What's our variable approaching? Pi, yeah, neither one of these approaches pi, right? Now, there may be some fancy way we could do a phase shift on this and make it work that way. But here. What now? Oh, for your guys, it would be Oya 2. Yeah. Yeah. Yep. But, but maybe we don't need to, right? Let's just see, is this thing even indeterminate, I guess, right? What happens here, it's written in terms of secant, so what do I probably want to do? Okay, 1 over cosine. So then I could write this as limit of theta, or phi, I guess I should say, over cosine phi as theta, or as phi approaches pi. Okay, so what do we get there? We don't get 0 over 0, do we? What do we get? On the top we get pi. On the bottom we get cosine. Oh, -1, you're right, yeah. I was thinking, yeah. So what's our answer? Yeah, we're done. Right? We're done. Remember, we said there's 3 kinds of outcomes we could get. When we try to directly evaluate a limit, either we're going to get an answer, right? We're done. Or we're going to get something else and we're done. What would that be? No limit. If I get a non-zero answer on the top and 0 on the bottom, then we can't divide by 0, and that's no limit. Done. Or we get indeterminate, right? And then we got to do more stuff. But this is actually an easier one in a way because we don't have to do anything, right? We're done. Okay. What else? Other questions on the sentence? Yes, ma'am. So you want to be able to, which one? Oh, okay. Yeah. What did I forgot what I even did for that. What did I do here? So if we go to which one? Where's that one show up? Oh, that was, okay, there isn't even anything on here yet, is there? Okay. Yeah, let's not worry about it yet. I'll put something up there. it'll just be a one question thing. I'll put something up and all you got to do is just, the criteria will just be if you did enough of the problems. This was on the stuff, well, this was the review assignment, right? What was this for?
It's kind of like you have to find the limit and then you have to prove if the limit affects and
Oh, okay, yeah. Which one was that on? Because we're not ready for that. Oh, that's this one right here. This guy, that's what I'm going to talk about today. Yeah, you guys can't do that one yet. Yeah, that's this guy right here, right? So I might need to change these dates, huh? 18. Oh, yeah. Oh, okay. Yeah, I was way off on that. Let me change the dates. That's not going to work. These other ones, do they? Well, remember, this isn't when it closes, right? These are just the recommended dates. Can you guys see when it closes when you go into it?
well, we see when it's due. Due it close, but it's due.
No.
Yeah.
No, you can see when it's.
We can't see when it's
Oh, that's weird.
closes, but we can see when it's due.
Seems like you used to be able to do that. That's strange. Okay, so I will. How about if we do this then? Because see, look, you got, that's weird. You can't even once you start it, you can't see. Okay, well, how do you see it? But like, see, look, I want to show you something. Can you see this? Like, if I go to my view of this, I want to make sure you guys can see this. So, for example, on the 1.3 practice 3, so it's technically due, meaning I'd like you to have it done today, but you can turn stuff in. So you can work and change stuff with no penalty until the 22nd. You can't see that? Oh, huh, okay. It doesn't say anything on there about that?
So if it just shows the due date, is it safe to assume that it's not due until like at the end of the week after that?
Yeah, let's just right. What I'll do, how about if I just add a calendar on Moodle that'll have all that information on it. I can't do it. That's one thing I can't do on Math Excel. It used to tell you. It used to say when you go into the assignment, students could see when it was due and how long they could change it. But it evidently doesn't do that anymore. Okay, so I'll add a little calendar on our Moodle site where it'll give you the recommended due date and the close date of the quiz or the assignment. I mean, okay, does that make sense? All right, so I need to change formal definition of a limit. Let's do 21st and 26th. How about? Okay, any other questions and everything up through the trig stuff? Yes, ma'am.
Did we do 8 and 10 on that one?
On that one too? Yeah, that's fine. Did that stick? Yeah, it did. Okay, good. Good. Okay, so there's something. So sine squared t over t squared. Let's look at that one. As t approaches 0. Okay, what I'm going to recommend here, what you guys tell me? Anything I could do right away here to maybe make this look better? But even just the way this is written is inherently a little bit confusing. The notation we use. What's sine squared t mean? What does it mean? Okay, good. So it's the quantity sine t squared, right? So it would probably help, and maybe this is all I need to do. Right? And there's really two ways I could go with this. You may want to suggest, well, let's go ahead and do this. Let's see. Anybody want to suggest one way we could go with this?
Square root.
Well, I can't square root, because if I square root, I'm changing the value of this, right? But I want to write it. Remember, I'm trying. This is indeterminate. If I try to evaluate it directly, I'm getting 0 over 0, right? So I've got to write this in terms of my special trig limits. Well, there's one. Which one am I probably going to use here? Sine t over t, right? Got an idea? Yes, sir.
No.
Oh, that's one. Okay, so how could I coax that out? I mean, really, there's a couple ways I could go about this. T times t. So I could split it apart, right? I could write this if I wanted to. I could write this as the limit of sine t over t times sine t over t, right? As t approaches 0. And we're not going to write the step out. Well, I will, but you don't need to. This, in our head, becomes two separate limits, right? But we know that the limit of a product is equal to the product of the limits. I don't really need to break this into separate limits, right? I could, though. What does this limit become? That one goes to 1, and this one goes to 1, right? 1 times 1 is 1. Okay? The other way I could do this, and now, tell me, did anybody do it this way? I'm kind of curious. I could write this as the limit of sine t over t, quantity squared also, right? We have a rule for that, right? We know that if we have a property of limits, if I have the limit of f of x to the n as x approaches a, let's just say that we know that the limit of f of x as x approaches a is L. What could I do with this then? If I'm taking a limit to a power. Say it again. No, I mean it's nothing tricky. Yeah, I could just write this if I wanted to as L to the n, right? If I'm taking a function to a power, right, then I could still just take this limit to that power. See what I'm getting at? So once again, we could just do this. We could say, well, I know as t approaches 0, the part inside the parentheses goes to 1, right? And so I end up with 1 squared. Well, what's 1 squared? 1. Okay? You see, either way it works. Okay, question?
For number 9, it's the same exact problem except for it's sine t squared.
Right, that's different, isn't it? That's different. If I have something like over t squared, right, or over t? Over t, okay. As t approaches 0. Okay, that's different, because what's implied by this? Okay, good, just the t is squared. So there are implied parentheses around the t squared, right? Well, okay, hold that thought. Hold that thought. Let me write the template down here, and then you guys suggest a way we could make this look like the template, because we have to use, the only way to deal with this is indeterminate, right? The only way to deal with indeterminacy for the trig limits is to harness those two special forms that we have. And, most of the time it's that first one. That's what's going to work here, isn't it? The limit of sine theta over theta as theta approaches 0 is 1. But it has to match that exactly. I have to have the same thetas every place in the problem. I don't have that, though, now, do I? Any ideas how I could get, well, what does my theta have to be here? What do you think? Not t. How come it can't be t? It's got to be, because look, that's the angle. That's what's inside the sine function, is t squared, right? You see what I'm saying? So that's telling me that theta has got to be that. So I've got to do some mathematical massaging of this expression here, so I can get the same theta that I have in the sine function. It needs to show up in my denominator and out front. But remember, I can't just do stuff to my expression to change its value. I have to maintain the value, which means really the only option I have is multiplying by 1 or adding 0. How could I multiply by 1 here in a way that's going to give me my theta of t squared on the bottom? T over t. Everybody see that? If I multiply this by t over t, I get that, don't I? Everybody agree? Okay, and then what could we say here? Richard, if t goes to 0, what could I say about t squared? It's going to 0 too, isn't it? Right? If t is approaching 0, then t squared must also be approaching 0, right? Actually faster, right? So I'm able to say that too. I can say, well, if t is approaching 0, I can just make that a t squared, because that also has to be true. Now I have, look what I've got there, right? I could break this into separate limits, and one of my limits is going to be sine theta over theta as theta approaches 0, right? Everybody see that? So really, this is, at this point, I can break this, and I'm going to write it out as separate limits here. Sometimes that's a good shortcut that you can take in the future, but let's break it apart this time. So now I've got this t by itself, right? I've got the limit of t as t approaches 0, right? We don't need to have t squared there, times the limit of sine t squared over t squared as t squared approaches 0. Does everybody see that? I can split that apart into those two separate limits. I'm just going to break that guy apart from those two.
Why
Right?
can you take the limit of t as it approaches 0
For one of them?
Yeah, but then the other one is t squared.
Because they mean the same thing, right? As t approaches 0, t squared approaches 0. So in this problem, it's convenient for us to look at the behavior of t squared. In this one, I could put a t squared there. It's just kind of awkward. Right? I don't need to, because I'm looking at the behavior of just plain old t. But these two things happen in tandem, right? They go together. If that's happening, then that's happening, right? And so if we're writing some kind of formal proof of this, we probably should say, okay, something like, well, if t approaches 0, then t squared approaches 0, right? Make sense? So what's the value of this limit? 1. What's the value of that limit? So what's the overall product limit? 0. Yeah. Okay. Make sense? And then what is the next one? I don't want to do two. I mean, I want to leave some of these for you guys to do too. Let's see. So 9's pretty similar. Okay. I'm going to leave this one for you to do. But you tell me, in this problem, what is my theta going to be? We can at least resolve that little bit. So if we're going to once again fall back on our special trig limit, what does theta need to be? It's got to be x, doesn't it? Because we're kind of locked into that, because the x is what's inside the sine function. Do you get that? That it's difficult to change the angle inside a trig function, You know, that's hard to do, right? There's ways to do it, but it's very complicated. It's pretty easy, though, just to multiply top and bottom by something to change the behavior of the bottom, right? So our theta is really dictated by what's already inside that sine function, right? So I got to multiply by top and bottom. It's really similar to the last one we did, isn't it? I got to multiply by top and bottom to get that theta on the bottom. One little hint. What is the cube root of x as a fractional exponent? X to the 1/3. Okay, so this could be rewritten as the limit of sine x over x to the 1/3 as x approaches 0. You take it from there. Okay. That ought to get started. Okay? So that ought to take us pretty well up through the trig limit stuff, right? Okay. I want to take just a little time today. Why don't you close those things up? I want to take a little time today, and I want to just talk about the formal definition of trig limit. Okay, so this is the stuff in your textbook. I'm just going to grab a picture of this. Right here, formal definition of a limit. Okay, so this is the part that I want you to understand. This is good for you guys to do because it's really important that you get to a point where this kind of math jargon in a textbook is comprehensible. So we want to try to understand what this statement means, right? So this is the formal definition of a limit. Let f be a function defined on an open interval containing c, okay? Except possibly at c. Doesn't need to be defined at c. So let's just take this piece by piece and see if we can figure out what this means. So what does this first part even mean? What's an open interval? What's that mean? Going back to like pre-calculus. What's an open interval? Like I could say something like, that's an open interval, right? What's that mean? Where x is what? Define where x is greater than a and less than b, right? So we got some range of values, some interval of values of x where our function is defined. Okay. It doesn't have to be defined everywhere, but it has to be defined on some range of values, or how can we take a limit, right? We looked at a bunch of examples earlier. I'll come back to this in just a second. We looked at a bunch of examples earlier where we did stuff like this, right? Where we just looked at graphs. And I said something like maybe something like that, and we had, remember this stuff, right? Is the function defined everywhere on that open interval? It is, right? Every place the ant walks that's greater than x, or an x value greater than a and less than b, he has a place to step, doesn't he? Right? And I asked you to find limits of certain places, right, on this open interval. So like, let's just say we said that was c and that was d. What's the limit if this is f of x? What's the limit of f of x as x approaches c in this case? No limit because there's a big break there, right? Large break. And this guy on the left thinks he's approaching that value. The guy approaching from the right thinks he's approaching that value. They don't agree, so there's no limit. Good. What's the limit what's the limit, same picture. We'll do it through, how about? Limit of f of x as x approaches d. Oh, let's just say that's 2 and that's 4, how about? 2. Right? Even though the value of the function is, whatever that is, 3, I guess, it doesn't matter. Ants from both sides anticipate stepping on a y value of 2, and so that's the limit, right? Good review, right? Okay. So our function is defined on this open interval. So that's all this is saying here. This is kind of the fine print on this definition. So our function is defined on some open interval containing the point C, okay, because that's the point that we're going to be approaching, the ant's going to approach. Remember, this is a key to the behavior of a limit. The function doesn't even have to exist at C, does it? Like I could go back to this picture right here, and let's make a little tweak to this one. Let's say, in this case, it's D. I could erase this point, and it doesn't change that answer, does it? Everybody agree? Because it doesn't matter where the ant actually steps. All that matters is where the ant thinks it's going to step, right? And both ants anticipate stepping on that point right there. Insofar as the limit is concerned, they never get there, though, so it doesn't matter. But where do they think they're going to step when they get there? They think they're going to step on a y value of 2, right? So the fact that it may not contain C is no big deal. As long as the function is defined at other places around C, so the ant can walk towards C, we're okay, right? Is that making sense? So this first part then, does everybody understand the rationale, why we got to say that stuff, right? In ant terms, the ant has to be able to walk along the function from both directions towards C, okay? And let's let L be a real number. So L stands for where the ant thinks he's going to step, okay? Get some answer. You can anticipate some number, okay? Then, what does this statement mean? That's what we're going to talk about. So the limit of f of x as x approaches C equals L. Tell me in terms of an ant definition. Okay, as the ant approaches next value of C, okay, it thinks it's going to anticipate stepping on a y value of L. Okay, good. That's all. Honestly, 99% of the time, that informal definition of a limit that you guys understand based on the ant definition is all you need. That's what you use. Okay, but mathematicians need to be able to define this in a bulletproof way. And so we're going to take this a little step further. We're going to do a formal definition. Sometimes it's called the epsilon delta definition. What this really means is that for each value of epsilon, non-zero, greater than 0, there exists a delta greater than 0 such that this stuff is true. Okay, now let's look at what this stuff means. This looks a little strange. Such that the absolute value of x minus c is greater than 0 and less than delta, and the absolute value of f of x minus L is less than delta. What is that? Okay, well, let's look. So if we look at our picture here, what does an absolute value really mean? If I say something like the absolute value of x minus 5, what am I really saying? Like on a number line, what would that represent? Okay, pause. Okay, but if I say something like this, let's go back. This would be kind of algebra 2 stuff, right? So if I say something like the absolute value of x minus 5 is equal to, at first, 1. What am I saying? Okay, so the way we solve this, right, we isolate the absolute value, already done, whatever's in the bubble, right, whatever's in the absolute value bars, that's either has to equal 1 or it could equal negative 1, because the absolute value bars make it positive, right? So either that equals 1 or whatever's in the bubble equals negative 1. Okay, so I can solve those. If I add 5 to both sides, I either get x equals 6 or x equals 4, right? If I add 5 to negative 1. Okay. What does that look like on our real number line? Isn't that like saying, okay, if this is the number 5, then these are those are my solutions, right? What's unique about those? How far are they away from 5? 1. Okay. So an absolute value is a distance on a number line, isn't it? Right? Look where the 5 comes from. X minus 5, well, there it is, right? That's the point that we're judging our distance relative to. And we want the points that are a distance of 1 away from that. See what I'm saying? Does that make sense? So if I were to say something like, let's say the absolute value of x minus c is less than delta, what am I really saying? Good. That I want the points x, now this time it's a less than, right? I want all the points whose distances from c are less than, that's a delta. It's just a weird Greek letter, right? Weird Greek variable, right? Does that make sense? So if I were to graph that on a number line, wouldn't that just look something like this? I've got my center point at C, just like we had 5 up here, right? And I want all the values that are no more than delta away from that, right? So it'd be like saying this. All those values in there, wouldn't it? Everybody see that? Okay, hold that thought. We'll wrap this stuff up tomorrow. Keep working away. I'll move that due date off. This Mondays, we never get through enough stuff on Mondays. Do this for me though, before you go. In the textbook, I want you to go back and read the part on page 51 through 53. You're not going to get it all, but I'll talk you through it tomorrow. Read that stuff.